Alright guys, today I'm going to be going over the final exam review. I'm going to do 2 videos because I think they upload faster if they're a little shorter. So I'll do the first 35 questions and then I'll do the second 35 on the second video. And I had messed up previously, so I had to start over. So let me go ahead and erase the things that I've already started. I did the first 2. Okay, so organic chemistry is best described as the chemistry of blank. So when you think organic chemistry, this would underline. There we go. You should be thinking of carbon. Now my pen's glitching. There we go. Carbon. Everything in organic chemistry leads back to carbon, right? Carbon chains, carbon substituents, carbocations, everything we do with carbon, right? So the answer is D, because compounds derived from biological sources? No. Pharmaceuticals, I think they mentioned medicine like a few times the whole semester just as like a neat fun fact. And then petroleum derivatives does not even make sense. Okay, moving on. How many atoms have a +1 formal charge, right? So formal charge starts off with your total valence electrons, which is found in the periodic table columns, right? So, for example, let me go ahead and do this whole thing. So, the valence electrons minus lone electrons. So, like, each electron in a lone pair is a lone electron. And then minus bonds. That's how I count it. There's, like, a different formula for it where it's like, lone pairs times 2, and then bond numbers divided by 2, or something like that. It's just easier to think about it this way. So, fluorine is in column 7, right? The halogens. So, we're going to start out with 7 valence electrons, and then we're going to count 1, 2, 3, 4, 5, 6, 7. The bond only counts as 1. It's like, you see 2 lone pairs, right? So how come the bond is only 1? And that's because bonds signify that it's sharing electrons with the carbon, right? That's how bonding works. That's how they attach to each other. So we're going to do 7 minus the 2, 4, 6 valence electrons minus 1 bond. That gives you 0. So this has no charge. Chlorine is also a halogen in column 7, so we've got 7 minus 2, 4, 5, 6. Minus 4, minus 2, that gives us 1, right? That's a +1 formal charge right there. Then we're going to go to oxygen. Oxygen's in column 6 on the periodic table, so we've got 6 minus 2 lone pairs, right? So we've got 2, and then minus 3 bonds, right? That gives us 1. Oh, sorry, guys. Hello. I'm making an OChem video. Okay, sorry. Bye. Sorry about that. Okay, that's a +1 formal charge. Nitrogen, sorry, I've been going off of memory, but I don't remember where I think nitrogen's 5. Let me pull up a periodic table. Yes, nitrogen's on column 5. So we're starting out with 5 valence electrons. We've got 2, 3, 4, right? So minus 2 lone electrons minus 2 bonds gives us another +1 formal charge, right? Gosh, there's a lot in here. Okay. boron. And so the reason I'm looking at these atoms in specific is because if there isn't a charge given to you on a carbon, you assume that it has enough hydrogens to fill its needs, right? So we're never going to be worried about the carbons. Unless it has a charge, like if you were shown an image and it was like that, then you would count that one. But if it's not explicitly given to you, the good thing about carbon is that we can always assume it's good. So boron, gosh, I don't know what boron's in. Boron's in column 3. Okay. So we've got 3 minus no lone pairs, right? There's no lone electrons. So it's just minus 3 bonds. Now we're at 0. Nitrogen's at 5. Was in column 5, I think. Yes. So it's not showing you, but it's 1, 2, 3, 4. Double bonds, I think, are doubled. Oh, no, we messed up on this one. Here it is. Here's the problem. Okay, I didn't count that there's a bond right here to the hydrogen, right? So don't let that get you. So we've got 2 lone electrons and 3 bonds. So that's at a 0. This nitrogen is no lone electrons, right? It's still at 5. There's no electrons hanging off of it. There's only 4 bonds. That's at a +1 formal charge. Don't forget that when there's a little H here, that represents an N bonded to an H. Okay, so now we've got oxygen. Oxygen has 2, 4, 6, 7 total. So we've got 7 minus 6 lone electrons minus 1 bond, back at 0. Okay, this oxygen has 2, 4, 5, 6. So remember again when I told you O bonded to, I also did this wrong. Oxygen's in column 6. Sorry guys, give me a second to get my brain going again. So 6 minus essentially 7, we've got a -1 charge, right? Which is why every time oxygen only has 1 bond, you see that negative charge on it. And anytime oxygen has 3 bonds, you see a positive charge on it. Okay, anyways, so we've got oxygen is bonded to that hydrogen, right? So we've got 6 minus 4 lone electrons minus 2 bonds, that's 0. Okay, so that means we had a total of 1, 2, 3. So our answer is C. Cool. Moving on. Okay. 3 of the following are resonance structures. Identify the one that isn't a resonance structure. Okay, so what I do for these ones is I start with the first structure, and I do the resonance on that structure, if that makes sense. So what I'm going to start with doing is I'm going to take this double bond and toss it here, right? So essentially I'm going to make a double bond here. In doing so, these lone pairs are going to go to the carbon that now got ripped from its double bond, right? So that's going to give you a lone pair here with a negative charge. And then we look for the structure that looks like what I just drew. So I should see, perfect, the double bond here that I drew, and then the lone pair on this one. So you know that A and C can't be the answer because they are resonance of each other. So now I'm going to do another one. So I'm going to take this double bond and move it here. So I'm going to create a double bond there, and I'm going to move these lone pair electrons to the oxygen who is losing a bond, right? So then this is going to gain 2 electrons and that negative charge. Then we got to look for the one that looks like that. And it's this one. Here's that bond that I made. Here's oxygen with its negative charge. So that means D can't be it either. That means the only option left for the answer choice is B. And let's look at this. Where did we get stuff to form this double bond here, right? How did we move these lone pairs here and form a double bond? Like, what electrons were we moving? It doesn't make any sense. So, B is the answer. Okay, we're looking for the Lewis structure of sodium hydrogen sulfate. Okay, the number one thing, when you see a cation, it does not form a real bond. It's going to float off to the side of whatever it's supposedly connected to, right? It doesn't ever, you're not going to ever see an actual line. It doesn't exist. So anything that has an actual bond line, you can go ahead and eliminate. Okay, cool. So that leaves us with this and this one. Okay, so now let's look. What makes you think that hydrogen would pop off when there are negative oxygens nearby? Like, if this were actually to occur in a bottle, these electrons would grab that hydrogen so fast to complete their octet. Because they don't, even though oxygen is highly electronegative and is one of the safest atoms to put a negative charge on and leave it there and be okay, it still wants to be a complete octet. So it's going to take a hydrogen proton if it's there. So this cannot exist, meaning our only answer choice left is C. Okay, and then, that's just what the sulfate looks like. Okay, extra credit. What is the hybridization state of the encircled carbon atom in the following compound? So we're looking at this carbon right here, right? It's got double bonds. So how I remembered it is I want to give you this trick for when you guys see it on another test, but it doesn't occur for this particular one. If you see just one double bond, like if we were looking at this carbon, right? And it had one double bond and then a single bond to another carbon, that would be sp2 because of the double bond, right? Because this p means that one of the p orbitals is being used, and that's why it's no longer sp3, right? It's moved to sp2 because one p orbital is actually being used for a pi bond, right? And then if you see a carbon triple bonded to a carbon and then singly bonded, and we're looking at this one, right? This would be sp because 2 pi bonds are formed, right? Meaning 2 of the p orbitals are now being used for a bond, so it can't hybridize with the s anymore. It's just sp, right? So then you look at this and you think, oh, well, it's double bond, so it's sp2. However, there are 2 of them, right? You got a double bond here and a double bond here, and those are pi bonds, right? And pi bonds use p orbitals. And if there's 2 pi bonds, that means you're using 2 p orbitals. So take your sp3 hybridized minus 2 p orbitals, right? All you're left with is sp. So the answer for this one is C. Okay. Of the following species, which of these could serve as a Lewis base? Okay. I'm going to be honest. I need to check the definition. Lewis bases are electron pair donators. So it needs to have an extra electron pair to donate. Okay. Oh, wait. Lewis acid, or did it say Bronsted? I think the question was Lewis. Well, if it said Bronsted, I'll just remember it as a proton acceptor. I think it was Lewis. Okay. Yes, it's Lewis. Okay, so let's see. Who has... Okay, Lewis base. Extra electrons. Right? So, let's look at this. We've got nitrogen with 3 methyls. So, we've got a nitrogen, methyl, methyl, methyl. But to complete the octet, we need a lone pair, right? So, does that look like electrons that can bond? Extra electrons? It's just a lone pair sitting out there. So, we're going to look at all the other answers, but I'm pretty sure it's A, because we see the extra electrons. And if you're wondering how I know that there's a lone pair there, so everyone needs an octet, right? We need 8 valence electrons. So each bond is 2, 2, 4, 6, right? 8. You guys remember counting for that stuff? Anyways, now we've got boron to 3 hydrogens. Right? Boron already prefers 3 bonds, right? And I don't think it would have a lone pair. I know with the whole octet rule thing, but boron's weird. Boron is one of the few atoms that's okay not completing the octet rule. It's okay with having just 6 electrons. CH4. Okay, where are the electrons that we could share? Nowhere to be found. All right. Now, we've got nitrogen again, but this time it has 4 methyl groups and a positive charge. So if it's got a positive charge, does it look like it's got electrons to donate? Or is it going to want electrons? It's going to want to take electrons, which would then make it not a base instead of Lewis acid. So that's incorrect. Cool. It's A. All right. Which one of these is the strongest acid? This you'll use your pKa chart for. So I'm going to try to remember OH and H2, which I just remember off the bat, this is a base. Okay. And then I know that there is a pKa chart at the end of this table. OH, NH2, SEH, and then SH. Okay. I'll do my best to remember that. Okay. So let's look at all our ratings. We've got here we are. Oh, SH. That one for sure. pK 7.8. I don't think this is it just because there's a NO2 on the other side. Let's see if we can find one that's just OH. We can. So now we know so far out of our groups, our SH is winning. We need an NH2 which is unfortunately not on this pKa chart, looks like. And neither is our SCH. Our beryllium, I think. So right now, what's winning is our SH, right? So let's look. Are things that determine acidity, right? So you can look at your pKa chart to get off on a good start. So we can go ahead and eliminate OH because we know for sure at least SH is stronger than that. I know NH2 is a base. If we just look here, I know it's not on a benzene ring, but NH2 right here has a pKa of 40. So putting it on a benzene ring does not make it any more acidic, right? Because it's all about how stable it is. And if you were to take a hydrogen off of an NH2, you now just have NH, which is going to be a negative. And a benzene ring is so stable, it is not going to want the negativity put onto it from an NH group, right? So you need something that's highly electronegative, that's going to, polarize and take away that negative charge from the benzene ring. So right now, like I said, our sulfur hydrogen is looking the best. But we can also look on our periodic table, right? We talked about electronegativity. So we've got sulfur right here. Selenium is more electronegative. Oh, never mind. Electronegativity moves up and to the right. Okay, so it's not more electronegative, but we'll look at our rules of... Oh, Lord. We'll look at all the rules for acidity and break it down. Bookmarks. Acids and bases. So strength of acids is based on size. So you move down the column. Here's a good example. Sulfur is smaller than selenium. So size would come first. And then we look at electronegativity. And then hybridization state, inductive effect, resonance, right? Leveling. So all those. But looking at this first. So we'll go back to our periodic table real quick. So if the difference in electronegativity was vast, then electronegativity would beat size. However, this is one jump away. Right? Because electronegativity moves like that. And, we're one square up. It is not that much different in terms of electronegativity. Okay? But as far as size goes, let's look. It's kind of hard to see. But we went from 32... right, 32 AMU to 79. So selenium is significantly larger than sulfur. So as far as acidity goes, it's not that much more electronegative, but selenium is significantly larger. So selenium is going to win out in that battle. And we knew that this wasn't it because it had a pKa of about 10, and this one's pKa was about, I forgot. I think it's like 7. And we know that NH is a base. Okay, so now we're looking at this again of the encircled protons, which one is the most acidic. So, cool, we've got another OH, so we know that pKa is about 10. And then if we look I hope you guys just have a pKa chart next to you guys, because I don't want to keep flipping back and forth, so I'm just going to use the one that's next to me. I hope you guys understand. Anyways, so we're going to look at an H connected to a benzene ring, and that pKa is 43. Not very acidic, right? So now we're going to look for a CH3, and just a normal CH3 connected to a CH2, right? If you look on your periodic table, just for a plain old Jane CH3 bond, our pKa is looking at about 50. I know the one on 50 is a CH3 to a CH3, but there's not, a whole lot of difference between a CH2 and a CH3. Other than, it's bonded to an extra carbon, but carbon doesn't give it any more acidity. So this one's about 50. And then you want to look for an NH2 connected to a CO and then CH. Kind of moving down there. So, really you want to see an NH2 that's connected to a CO. Quickest one I found has a pKa of 16. It's on the farthest right column, kind of in the middle. Or actually towards the top, sorry. Yeah, it's like 5 down. Okay, so now let's look at all of our pKa's. 10 is the lowest, and the lower the pKa, the more acidic. Okay, moving on. Select the mechanism that best represents the reaction to the right. So, rules about arrows. They start at electrons. So let's see if any of them start. This starts at an atom. Wrong. Okay, see how this starts at electrons? Bonds are just representations of sharing electrons, so that also starts at an electron. That looks like it's starting at the charge, instead of pointing more so at the actual electrons, so I'm not really feeling that one. And to be honest, I'm going to go ahead and get rid of it, because you see how this is like very clearly pointing at that. This one is pointing at the charge. The charge is just a representation of the fact that it's negative. We want to be pointing at the electrons. And this is pointing at an atom. So that one's wrong. So our best answer choice is B. Cool. So you don't necessarily need to understand the actual reaction that's happening. Because I don't think, most of the time he's got it pretty obvious that it's not pointing at the electrons, so that just means the drawing itself is wrong. But, so let's look. We've got our HCO3, right? And then our H3O plus here. So we know we go from H3O plus to H2O. So let's see. This hydrogen is being ripped off, and it's giving the electrons back to this oxygen, which is going to make it just an H2O. Meanwhile, if this gets taken over there, we'll end up with H2CO3. Okay, moving on. Which one of them is an ether? Ether has a carbon on ether side of oxygen. Let me take a drink real quick. Sorry, my mouth is getting a little dry. So let's look. Here's an oxygen. We're missing a carbon. Can't be D. Oxygen. Where's the carbon? Can't be B. Oxygen. Missing a carbon on the other side of it. Okay. We have an oxygen. Carbon here. Carbon here. We have an oxygen. Carbon here. Carbon here. Okay, so now let's think. Out of these, which one could it be, right? Because technically they're all meeting the requirements, right? However, this has a double bonded O to it, and I think that makes it a carboxyl group. It's not a carboxylic acid because it's got an extra carbon, but this is I think it's just called a carboxyl group. This is a oxygen double bonded and it's got carbons on either side. It's a ketone. This is our ether, and this is an aldehyde. Actually, yes it is. Because it has a hydrogen bonded to the other side. So that's an aldehyde. Okay, cool, C. All right. Which one is a secondary alcohol? Secondary alcohol means we've got an OH bonded down here. This carbon is bonded to two carbons. That's what makes it secondary. If it was primary, the carbon it was bonded to would only be bonded to one. If it's tertiary, the carbon it's bonded to would be bonded to three. What did we just talk about? It's bonded to one. This is primary. Oh, hey, looks just like what I drew. Two carbons. This is secondary. Carbon it's bonded to only has one. This is primary. And then this is just a carboxylic acid. But in terms of what we were talking about, bonded to one would have been wrong anyways. Okay, I'm going to start moving a little bit faster because there's a lot of questions to get through. What is the maximum number of hydrogen bonds that one water molecule can form? 4. Let's see them. Oxygen, 2 lone pairs. Hydrogen, hydrogen, right? Technically, we have more water over here, water over here. These could bond like that. Could take a hydrogen with those lone pairs. So you're not going to see water bonded to 4, but it could. Just not very likely. All right. Least soluble in water. You see these? That lets you know it's a salt. Salts are very soluble in water. Okay. So now we're looking on to A and B, right? OH, NH, FH. Can hydrogen bond? Meaning, it would be soluble in water, right? If it can bond with hydrogen, it can bond inside the water. This has 1 OH. This one has 3, making it better. B. Cool. Which of these species does mass spectrometers analyze? This is a definition question, and I want to say it's ions. It's not resonance stabled. It's not radicals. I don't think it's isotopes. I think it's just ions. Yep. Okay, when analyzed by mass spec, a compound was found to produce 2 molecular ion peaks, so-called M+2 peaks. Okay, in a 3-to-1 ratio. What did we talk about? M+2, that lets you know it's either bromine or chlorine, right? 3-to-1 ratio was chlorine all day. 1-to-1 was bromine. So, alkyl chloride. Wasn't fluoride. We never talked about that. It wasn't iodide. Bromine is 1-to-1. Okay, which one of these is the mass spec? So we know our final is about, this is 50, 55, 60, 65. Okay, so this is 160 here. So we know our molar weight is about 159. And our base peak, I believe was the term for it, is at just about 76-ish. Okay. I'm not seeing an M+2 peak here. Are you guys? So I'm going to go ahead and eliminate. Actually, hold on. We're looking at these big ones. We got 1, 2. Okay, this is an M+2 peak. Wrong. You go with the last ones. Sorry, guys. But this is also an M+2 peak. These tiny ones down here. And they're like the same height, so that's 1-to-1 ratio. Which lets you know it's not chlorine, because that would have been at a 3-to-1. So it has to be bromine. It's kind of hard to see because we've got peaks in between it, but you go with the very last ones. Okay, and then we know that at about 76 is our base peak, so let's double check it, right? We've got 1, 2, 3, 4, 5, 6 carbons. 6 times 12 gives you 72, plus 1, 2, 3, 4, 5 hydrogens. Puts us at about 77. So good. That's where our base peak was. Okay. This is a spectrum of cyclooctane. What is the peak with at 113 called? So this one. Pretty sure that's our M+1 peak. What are you guys thinking? It's the very last peak, and it would be M+2 only if we contained chlorine or bromine, and there was a gap between them, right? They're like one after another, so that's M+1. M+1 peak is caused by the carbon 13, right? You guys remember that? Okay. Which side of the spectrum represents higher energy IR radiation? Okay. What are you guys feeling? Let's look at our numbers. 500 to 4,000. So, which one's higher? The left side, right? Okay, which one produced the following IR peaks? Okay. So you guys will get an IR. Here, let me go to it. We're looking for a peak, right? Relatively at 3,000. Okay, cool. So, at about 3,000, what we're seeing is... Oh, he doesn't give you all of these. Anyways. Carbon sp2 hydrogen bonds, right? So it's about 3,000. It does go a little over, which is good. And then, you know, sp3 bonds. So if it's sp2, what did we just talk about? That means a carbon double bond. OH, there was a couple answer choices of that. That means we would see it at 32 to 36. Where were we? Also, if it was an OH bond, it would look way more like this than that pokey. So, we know that we've got a double bond. This is a triple bond. This has no double bonds, and we don't see the OH peak. We did not see the big, broad OH peak, so that one's also out. Here's our double bond. Okay, which is the IR we see. Okay. Again, we don't see the classic nice and pretty rounded. So for these other ones, the reason that it would get a little wonky would be because of the neighboring bonds, right? So, okay, I'm going to stay here and just pull it up on my laptop. The IR chart. You guys are going to have it on the test, and I'm sure you guys know how to read it by now. So, if it was, this right here is a carboxylic acid, right? And there's a chart for that. So the carboxylic acid is going to have a strong peak at about 1700 for the CO. And then for the OH, it's going to be at about, 25. Get out of here if you're going to bite me. Get out of here. To 35. Right? Okay. Which, about 25 to about 35-ish. And then we see 15, 16, 17 strong peak there. Perfect. You got our answer. It's a carboxylic acid. Which is this guy over here. I don't know why I read that as an OH. That's not a carboxylic acid. And this is just a ketone. Also not what we're looking for. So our answer choice is B. Just looked down away from my IR chart and saw whatever madness I was looking at. Okay, so let's get this again. Looking at the IR chart. Okay, so let's just look at something that would be easy to find on the chart. So C to a nitrile, we're looking at about a 2250, which would be like up here. So we do have a small peak right there pointing to it. Which there's no other peak for. So answer choice is B. And then this over here is the same. Not the exact same, but remember we were talking about those sp carbon hydrogens. Carbon hydrogen sp bonds are about 33,000. And sp2 IR is never perfect. I know the hydrogen bonds aren't where we expect them to be, but it's never going to be perfect. But we do for sure see our nitrile. Okay, IUPAC name. I'm going to go ahead and make this into a cyclohexane. I think it makes it easier to see. Okay, and I'm going to number 1, 2, 3, 4, 5, 6. Okay, remember we said up was bold. Down is dashed. So on carbon 3, 1, 2, 3, 4, 5, 6, I've got a bold methyl, and on carbon 5, I've got a dashed, which does make it trans, not cis. And yes, I have it numbered 3, 5. But if we switch the numbering scheme, because you can number it however you want. 1, 2, 3, 4, 5, 6. You always want to go with the lowest possible numbering system. So 1, 3 is the better option. Even if you have to number your thing differently, because technically 3, 5 is still correct, but that's not how IUPAC numbers. You always want to go with the lowest possible numbering scheme. Okay, Newman projections. We said when looking from the left, excuse me, guys. Bold is to the right. Dashed is to the left. And inverse, right, when looking from the right, bold is to the left. Dashed is to the right. Okay, so we're looking from the left, though. See how this is on the left side? Okay, so that means this bold methyl should be on the right side. There's a hydrogen there. That's wrong. Methyl, that one checks out. That one checks out. Hydrogen, that one's wrong. Okay. And we know if there's a bold methyl, there's a hydrogen on the left. So I should see hydrogen on the left, hydrogen on the left. All right? And up above, we've got a methyl. Okay. We've got a methyl on a dashed, which means it should be on the left. We've got a hydrogen on the left, unfortunately. Here we go. Methyl on the left. Answer choice is C. And then chlorine at the top. Chlorine at the top. Okay. Lowest energy conformation. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is axial. This is equatorial. This is equatorial. This is equatorial. Axial, axial, equatorial, equatorial. However, 1, 2, 3. These are on the wrong carbons. So I went ahead and just got rid of D. All right. I'm going to go ahead and draw these. So we've got chair 1, chair 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. We said bold was up. So we've got up, up. And dashed was down, down, down. So we should not ever be axial and equatorial at the same time, because on both of the ones I drew, we were either ek and ek or axial, axial. So this is not a low energy conformation. Axial is the highest. So right answer should be B. Okay, heat enthalpy, what can be concluded about the relative stability of the two compounds? Heat enthalpy and the stability of the compounds. I don't think you can determine that. Nothing about the heat of their combustion would tell you about how stable the compounds are. I'm going to go with D. Ooh, okay, that would have been embarrassing. Give me 1 second, guys. I'm getting cold, so I'm going to go grab a jacket. And recently, my iPad has not liked to charge at all. As you can see, the charge is dropping even though it's plugged in. Okay. How many of these are chiral? I hate doing these because it takes so long. Okay. First, we got to look for stereocenters, right? Not a stereocenter because there are 2 hydrogens. We need 4 unique. 1, 2 methyl groups, not a stereocenter. Hydrogen, this is a stereocenter. We're symmetrical, which means it's not a stereocenter because we've got the same substituents on both sides. Okay, so 1. Only one of these has a stereocenter, so only one of them is chiral. Cool. Moving right along. Unfortunately, guys, it's starting to look like you're going to get the first video, and I will try to do the second video tomorrow morning because my iPad is not cooperating very well. It's at 16, and I think when we started, we were at like 20. But we're going to finish these first 35. Okay. Let's find the longest carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. I don't think it gets longer than that. Octane, we're good. All right. So we've got 1, 2, 3, 4 methyls. And the word for that is tetra. So we're a tetramethyl compound. And we've got them on 2, 4, and then got both on 6. So we're 2, 4, 6 tetramethyl. Stereocenters, this isn't 1. 2 methyl groups. This is 1. This is not 1. Okay, so we've got 1 stereocenter. And we've got a hydrogen. I'm going to do these in different colors. So we've got carbon here, carbon here. This carbon on the right has number 1 priority because it's got the most carbon-carbon bonds on that side. This one has second priority because it has the second most carbon-carbon bonds on that side. This methyl group is priority 3 because it has nothing, and hydrogen's always priority 4. So, and it's in the back, so we're going to just go ahead and go right to the normal configuration. And this is moving counterclockwise, so it's S. So we are S2466 tetramethyl octane. So we can get rid of the R's. 2466 or 3357. This isn't the lowest possible numbering scheme, so that's wrong. Okay, relationship between the 2 following structures. 1, 2, 3, 4, 5, 6. 1, 2. Okay, 1, 2. Lowest possible numbering scheme. I just went ahead and jumped the gun and did it. So this is a 1,3 dimethyl cyclohexane. This is a 1,2 dimethyl cyclohexane. So they're not the same atom-atom connectivity, which makes them constitutional isomers. They're not diastereomers or conformers. There's nothing. They have different atom-to-atom connectivity. Okay? If a sample was found to present 20% EE, what was the ratio of major enantiomer to minor? Okay, so if 20 EE means 20% A, and 80% of A plus B, right? Which essentially means 40% A, 40% B, which really gives you 60% A because you add them together, and then 40% B. And then when you put that, you reduce that. And let's go ahead and do all of our math. Reduce that by, by 2. Then you, or I guess 20 to get rid of the zeros. Then you get a 3-to-2 ratio. Okay. All right. Looking at this, what is the best description for the enthalpy change for the overall reaction? So, number 1 represents reactants. Number 7 is our products. Our reactants have much more energy than our products. So if we lost energy going from reactants to products, that would make us exothermic, right? Because we gave off a bunch of energy. How many transition states? So the peaks of every hill is a transition state. So that means there's a total of 3. Numbers 2, 4, and 6. What's the best description of the following reaction? So I'm seeing a double bond form. If a double bond is forming, we are an elimination reaction. But if a double bond was breaking, that'd be addition, right? Okay. What is the enthalpy change? So this one, you need to use the other chart. You're given like a million, I know. The bond dissociation energy chart is what you need to use. So first we're going to see what bond was broken and what bonds were made. So we've got a CH to CH3 to a CBr CH3. So that means a CH bond was broken and a CBr bond was formed. We went Br2 to HBr, meaning a bromine to bromine bond was broken and a hydrogen to bromine bond was formed. So let's look at the energy it takes to break a CH bond. So we're going to look at our RR bonds and our RH bonds is what we're going to look at. So I want you guys to look 1, 2, 3, 4 at the 5th one in our RH bonds. Do you see how it says CH3 parentheses 3 C to H? And then the kilojoules per mole for that one is 381. Okay, now I want you to look at your ZZ bonds, and you'll see a bromine to bromine at 192. Now, look at your R to X bonds, and I want you to find, it's the second one from the bottom. So go to the bottom and go up 1. you'll see the 3 methyls bonded to a carbon, and then that carbon is attached to a bromine. That's at 272 kilojoules per mole. And then look at your HC bonds. You'll see H bonded to bromine. That's at 368. Okay. Now, this is bonds broken minus bonds formed. So essentially, reactants minus products, which is backwards. Usually, we always do products minus reactants. Not for this one. Okay, so we're going to add 381 and 192. That's 17, 3, 5. Okay, then we're going to do 272 and 368. 10, 14, 6. Okay, now I know that my reactants is lower than my products. So what I'm going to do is products minus reactants, but I know it's going to be negative. Oh. That was the 3. So we're at negative 67 kilojoules per mole, which is D. Don't get it twisted, right? If you do what I do, where if the number is bigger, that's the only way I can subtract on paper. I don't know how to subtract a smaller number from a bigger number, writing it out. So I always put the bigger number on top, and then I just know that it's going to be negative because the products was bigger than the reactants. Okay, 2 more. What is the most effective leaving group? I honestly, just gut reaction, want to go with chlorine, because chlorine is what I always see. But let me think about the rules again. So I know OH does not make a good leaving group. If it was OH2 plus, that would make a good leaving group. But OH by itself doesn't. So the weaker, this is why, I remember. The weaker the base, the better the leaving group. Okay, OH is a strong base, right? Well, not super strong, but hydroxy is a pretty strong base. NH2, we just talked about how that's a base. So, chlorine and iodine are both part of a strong acid, right? Hydrochloric acid and hydroiodic acid. Right. But what is the strongest? Well, I shouldn't say the strongest because they're both strong acids. So now we got to look at something different, right? What else would make it a better leaving group? So iodine is really big, right? It's a really big it's a big atom. And I could be telling you guys the wrong thing, but I think it makes its bonds a little, not weaker, but kind of less stable. Because it's so big, it has a harder time, with that bond. So I going with my gut here. I think iodine is better than chlorine. Okay, cool. Last one. Most effective in an SN1 reaction. SN1 like secondary and tertiary alkyl halides. You're never going to do something like that because the benzene ring is so stable it's not going to want to react. This is a primary, not stable. This is allylic, not doing that. 1, 2, 3, tertiary. That's perfect. Answer C. Okay, so that's going to be it for today. I will do my best to do the rest of the other 35 tomorrow morning. I know you guys have your final Friday morning, so I will do my best for you guys. If you guys have any questions while studying, feel free to reach out. I'll always do my best to answer any questions you have.